Hi everyone, my name is Jakub Staroń. This is the next episode of MedChem Essentials, scientific seminars devoted to medicinal chemistry. Today we'll be talking about volume of distribution. This is part of the second section of our course related to half-life. Today we'll talk first about body compartments, then compartmental model, then about blood flow in the organs, and finally about the core concept of volume of distribution, and we will finish with a practical example illustrating the concept of volume of distribution. Let's start with body compartments. When we talk about the body and the concentration of the drug, it's impossible to treat the body literally as it is because it is just too complex. So, in order to simplify things, we are approximating the body into compartments. And the most simple approximation of the body is the one compartment model, where we treat the whole body as a single reservoir for the drug. So this is applicable for drugs that distribute rapidly throughout the body and for drugs that do not distribute throughout the whole body but are largely confined within the, let's say, vascular system and the highly perfused organs. So after the administration and distribution is complete, the concentration of the drug exponentially declines to zero. So when this is plotted over the semi-logarithmic plot, we see a linear decline of the concentration of the drug with time. The second approximation is the two-compartment model. Here, we are simplifying the body into two compartments. The central compartment, composed of organs that are highly perfused and equilibrate rapidly. So this is the plasma and these highly perfused tissues like kidneys, lungs, liver, heart, and sometimes for individual drugs also the brain. And the second compartment is the peripheral compartment, composed of skeletal muscles, fat tissue, and other organs that equilibrate slowly and are lowly perfused by the blood. When we are talking about the drug concentration, changes of the drug concentration in time for the two compartment approximation, we see two distinct phases. So after intravenous administration, first is the steep decline of the drug concentration because the drug is getting distributed throughout the body. And after the distribution is complete, we see on the semi-logarithmic plot, a linear decline of the drug concentration. On this slide, we see different organs and assigned values of blood flow and perfusion rate. So clearly, we can categorize organs into two groups. First one is the highly perfused central compartment. We talked about it with high blood flow and high perfusion rate. And the second is the peripheral compartment with low perfusion rate and low blood flow through the body. So now let's talk about volume of distribution. In the, let's say, single compartment approximation, we have a reservoir. This is the body, and a drug is placed in the reservoir. So in a particular volume of the reservoir. So there is an amount of the drug placed in the volume of the reservoir of the body. And we have the extractor organs, kidneys and liver mainly, which constantly drain the reservoir from the drug. So the concentration of the drug is based on the amount delivered and the volume of the reservoir. And after the distribution phase is complete, the concentration is a function of a dose and the extent of distribution into tissues. So we can imagine that when we administer the drug and some of the drug gets absorbed, distributed in the peripheral tissues, then the concentration in the plasma drops. So the concentration in the plasma will be a function of the distribution, also of the extent of the distribution into tissues. What we are actually measuring will be the volume of distribution. What we can measure is that we know the amount of the drug delivered, we know the plasma drug concentration, so we divide one for the other, and we get volume of distribution. So drugs that are distributed poorly into the peripheral tissues, the peripheral compartment, will have low volume of distribution, and drugs that have a high extent of distribution into peripheral tissues will have high volume of distribution. Let's see some practical example that will illustrate the concept. So in a single compartment model, again, let's assume it has 1 liter volume. To this 1 liter of volume, it contains 10 grams of activated charcoal, and the charcoal will represent the peripheral tissues. We administer 100 milligrams of the drug. And after some time, after the equilibration distribution is complete, 99% of the drug gets absorbed into the charcoal. Then we can calculate volume of distribution. So we will have only 1 milligram in the reservoir, in the plasma, let's say the volume, because 99 milligrams got absorbed into the charcoal. So we have 1 milligram divided by 1 liter, this is the concentration. So we take the dose divided by the concentration. This is 100 divided by 1, it's 100 liters. So you see the volume of distribution of this drug in this case will be 100 liters. So it is 100 times greater than the actual volume of the system. Amazing. But volume of distribution quite rarely corresponds to the physical volume. The volume of the plasma is 3 liters. Volume of the extracellular water is 16 liters, and the total body water is 42 liters. And some drugs exceptionally can have 100 liter like this volume of distribution when they are quite lipophilic and gets concentrated and highly absorbed and distributed into the peripheral tissues. But about this we'll talk about next time. So thank you very much for your attention and see you next time. Bye bye.